we've talked about electrons, and we talked about the Bohr model and how the Bohr model anticipated that these electrons were spinning around the nucleus on these levels, or energy levels, right? And then we expanded that a little bit when we looked at the house model, where we had the sunny room and the pink room. We talked about how they're not really in these specific levels, but there's actually these things called sublevels. And we gave those the names orbitals. If you haven't done that POGL yet, you'll need to pause or just know that a lot of this information is in that POGL. So first off, we're going to talk about what an orbital is, and then we'll practice some electron configuration and orbital diagrams. All right, so first, what is an orbital? An orbital is a graphic representation of the space that an electron will occupy 95% of the time. When we talk about orbitals, we talk about them as though that is where the electron is for sure, but that's not true. Okay? An orbital is where the electron is 95% of the time. It is not a physical construct. There's no walls on the orbital to keep the electron in. It is a concept. It is where the electron will be 95% of the time. Okay? And how do they know that? So they have a way of locating the electron within an atom, and they located it over time in all of these places that you see a dot. So they located the electron, they went back and located it again, located it again, located it again, and then they say, okay, 100% of the time the electron's in one of these places. However, 95% of the time the electron is in this area. So this area is known as the orbital. And for the 1s orbital, or any s orbital, that orbital is in the shape of what we call a sphere. Remember that atoms are three-dimensional, so you can imagine that is not just a circle, but a sphere. Different orbitals they found have different shapes. But an orbital, again, is where the electrons are found most of the time. That orbital can leave. This dotted line is just something that we draw on the atom. It's not actually there. All right. So, there is another depiction of the 1s orbital. And again, there are many, many different orbitals where the electrons can be found. But the first two electrons to enter an atom will be found in an orbital of this shape 95% of the time. All right. So, how do electrons go into the atom, or where are they found on the atom? Well, electrons are added to the lowest energy orbital available. This is because nature always favors low energy systems. So throughout chemistry, when we talk about energy, if we want a system to increase its energy, we're going to have to do some work, because nature always favors the lower energy system, or the lowest energy construct possible. So we have a format that scientists have figured out that can be followed to determine what is the lowest energy orbital available. Because we say the electrons are going to the lowest energy orbital available, but which is it? Right? So, lucky for us, the periodic table really tells us where the lowest energy orbital is. And this periodic table shows you how the electrons go into the orbitals. So we start up here, just like if we're reading a book, we start to the left on the first line. So the first electron goes into the 1s orbital. So there would be one electron there. When you get ready to add the second electron, it also goes into the 1s orbital. So there are two in the 1s orbital. From there, it will go into the 2s orbital if we have 3 electrons. So 1 electron, 2 electrons, 3 electrons. If we have 4, that next one can also go into the 2s. As we move over, we now have a p orbital on the second row, so 2p, and it can actually hold 6 electrons, which you see there. After that, we have 3s, if we have more electrons, and then 3p. We then have 4s, if we have more electrons, and after that is filled, we actually have the 3d orbital. Now, this can be a little bit confusing because we went 4, it seemed like we were going in order, right? 1, 2, 3, 4, and then we have the 3D. This section is our D section of the periodic table, and in that section, this number, this energy number, is always 1 less than your row. So if we're on row 4, we go 4s and then 3d. On row 5, 5s and then 4d. So you see they're always 1 less than your row number. After 3d, we would put electrons in the 4p, then the 5s, 4d, 5p, then in the 6s. Now something funky happens right here. If you look at your periodic table, between these two, the 6s and the 5d, we actually skip a bunch of numbers in terms of the atomic number. And that is because we need to go and add in this F sublevel, and it actually fits right there on the periodic table. The reason we don't see it on the periodic table is because it would make the periodic table really, really wide. Okay, this is actually an example of what it would look like if we took the F sublevel, which is this part right here, and inserted it where it should go in the periodic table. So the only reason we don't do this is simply because of space. So they just cut this out, because these elements are pretty rare anyways, and moved it down there so that the periodic table can fit on a piece of paper. That really is the entire reason behind it. All right, so looking back at our order, we would go 6s, and then we would go down to the 4f, and then when we finish with 4f, we would come back to 5d, and then go through 5d, 6p, 7s, then down to 5f, then back up to 6d, and then 7p. So this is the order in which we're going to fill up the orbitals. So you saw those first few on the POGL, but this is the rest of them. Okay, so we'll look at a few examples of what that looks like. For hydrogen, hydrogen has 1 electron. So that 1 electron is going into the lowest energy orbital available, and that is the 1s orbital. So hydrogen's, what we call electron configuration, is 1s1. Let's talk about what that represents. This 1 is the energy level, also known as the principal quantum number. The s is the orbital type. So in this case, it's s. Remember, there's also p, d, and f. And then our exponent tells how many electrons are in that sublevel. Hydrogen only has 1 electron, so it goes into that lowest energy 1s orbital. For helium with 2 electrons, those 2 are both going into the 1s orbital. So it's 1s, but instead of 1, like hydrogen, it's squared, because there are 2 electrons in that sublevel. Okay, and again, this is called the electron configuration for helium. Moving on to lithium. Lithium has 3 electrons, so we put 2 in the 1s orbital, so it's 1s squared, but that's all it can hold. So then we can put the third one into the 2s orbital, so that would be 2s1. Notice the 2 plus 1 is 3 electrons total. 2 of them go in the lowest, and then when it's filled, they'll go in the next lowest, which is the 2s. This, what you see over here, is called shorthand or noble gas notation. It is written by taking an element from the very last column. So those elements are from group 18, and putting it in a bracket, and then starting there with your electron configuration. So for lithium, the noble gas, or the group 18 element that comes before lithium, is helium, which is 1s2. So instead of writing 1s2, we just insert helium, and then whatever would follow. So in this case, 2s1. All right, beryllium comes after lithium. It has 2 electrons in the 1s and 2 in the 2s, because it has 4 total. So those first 2, as always, go in the lowest energy orbital, and then it has 2 left to go in the next energy orbital. So this is the electron configuration. If we wanted to write that shorthand, we could replace this 1s2 with the element helium, because that is helium's electron configuration, and then finish out beryllium with the 2s2. All right, carrying on from there, we see some more examples. So we have boron, which has 5 electrons. So 2 into the 1s, 2 into the 2s, and then 1 into the 2p. And again, you see the shorthand with helium replacing the 1s2. We get another electron for carbon, and it also goes into the 2p. Nitrogen adds another electron. It has 7. And that one goes into the 2p as well. Oxygen has 8 electrons. So 2 into the 1s, 2 into the 2s, and then 4 into the 2p. So there's our electron configuration and the shorthand. Fluorine has 9 electrons. So 2 and 2, and then 5. Neon has 10 electrons. So 2, and then 2, and then 6. At this point, our second energy level is filled. Neon is at the end of the second row, and that P can only hold 6 electrons. So the 1s, the 2s, and the 2p are now filled, and that fills the entire second energy level. So we move down to sodium, which has 11 electrons. We'll put 2 in the lowest, 2 in the next lowest. The next one can hold 6, so there's 10. But that 11th one is going to have to go in the next sublevel, the 3s. Again, we can write the shorthand, but it's a little different this time because the noble gas or group 18 element that comes before sodium is neon on the periodic table. And neon, if we look back, is 1s2, 2s2, 2p6. So we can rewrite that by getting rid of all of this, which represents neon, and just plugging in neon and the 3s1 that comes after it. All right, let's look at 2 more that are a little bit more complex, and you can use all of these examples as you do your own practice problems. So we're looking now at scandium. Scandium is element number 21, so it has 21 electrons. I want to go find it on the orbital filling table so we can get an idea of how we would do a long element like this. All right, so scandium is located right here on the periodic table. So its electron configuration would be 1s1, 1s2. That one gets filled. 2s1, 2s2. 2p1, 2, 3, 4, 5, 6. That one is filled. 3s1, 3s2. 3p1, 2, 3, 4, 5, 6. We got to make our way all the way to scandium. 4s1, 4s2, and 3d1. So the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1 would be the electron configuration for scandium. All right, and that's what you see on the screen there. Now the shorthand becomes especially useful as we get into these larger elements. So if we look on the periodic table, the noble gas or group 18 element that comes before scandium is argon. And argon's electron configuration goes all the way to 3p6. So we can replace all of this with the element argon and then add 4s2, 3d1 to specify scandium. The next example is for the element samarium, which is element number 62. Okay, I'm not going to walk through this one in as much detail, but I will point out a few things. After 4s, we have 3d, followed by 4p, then 5s, then 4d, then 5p, 6s, and then notice after 6s, we have that 4f. We can do the same thing with this super long electron configuration. We can shorthand it. Xenon is this electron configuration up to 5p6. So we can replace all of that with the element xenon in shorthand. All right, so that is how we do electron configurations.